A sequence b0, b1, b2, ... is defined by letting b sub 0 equal 5 and b sub k equal 4 plus b sub k minus 1 for each integer k greater than or equal to 1. Show that b sub n is greater than 4n for every integer n. We're going to prove this with mathematical induction. And so the first thing we're going to do is identify what p of n is. P of n is going to be this propositional statement: b sub n is greater than 4n. We're going to start with our base case, which is what we get when we plug 0 into p of n. Now, I should mention that we're assuming this chunk right here. Now, before we get to the base case, it's important to note that this part right here is an underlying assumption about our sequence. Now, for the base case, we're going to replace all of our n's in p of n with the number 0. So we're plugging 0 into this blue part right now. To avoid asserting the conclusion, I'm going to add a question so that I don't assert the truth value of the statement. We want to prove that the truth value of the statement is true. Now, b sub 0 equals 5, and 4 times 0 equals 0. So we can see that 5 is greater than 0, which means that b sub 0 is greater than 4 times 0. Now, the beginning of our inductive step is going to be the same. If you notice, I'm reusing a local variable k. K is a local variable, and the locality is within the inductive step, whereas k in the definition of the sequence is a local variable. So that's why these two letters here are the same, but they represent two different variables. Right now, we're in the inductive step, so this letter k represents an instantiated arbitrary integer that is completely separate from this local variable above in the definition of the sequence. So p of k would be b sub k is greater than 4k. So we get to assume that this is true. And that's our inductive hypothesis. We want to show that p of k plus 1 is true, which means we want to show that b sub k plus 1 is greater than 4k plus 1. Now, to show that, we're going to start with the left-hand side of p of k plus 1. So that's b sub k plus 1. Now we can use the recursive definition for our sequence, which states that any term can be found by adding 4 to the previous term. So b sub k plus 1 is equal to 4 plus b sub k. And that's by definition of the sequence. Now we have a b sub k. Now we know something about b sub k because of our inductive hypothesis. We know that b sub k is greater than 4k. So by our inductive hypothesis, this means that 4 plus b sub k is greater than 4 plus 4k. Since if we replace b sub k with something smaller, 4k, then overall 4 plus 4k is going to be smaller than 4 plus b sub. Another way you can get this inequality is by adding 4 to both sides from the inductive hypothesis. So it's important to assert that we know this to be true by the inductive hypothesis. There's no other way we can prove this. Now we can take 4 plus 4k and we can factor out a 4 to get 4 times k plus 1, which is the right-hand side of p of k plus 1. So let's summarize what we've shown. We started with the left-hand side of p of k plus 1, which is equal to b sub k plus 1, which is equal to 4 plus b sub k, and we showed that that was greater than 4 plus 4k, and 4 plus 4k is the same thing as the right-hand side of p of k plus 1. So altogether, if we follow this chain here, we get that the left-hand side of p of k plus 1 is greater than the right-hand side of p of k plus 1, which implies that p of k plus 1 is true. And then we can end this proof by stating that by mathematical induction, the statement p of n is true for all integers n greater than or equal to 0. Thanks, everyone, and I'll see you in the next